Hi there, I'm Dr. Fang Xu. Today, let's talk about solution and electrolyte. I guess you're all familiar with salt, which is sodium chloride. When you dissolve salt in water, or when you put the salt in water, you have this glass of salty water, which is transparent and in a solution. Have you ever wondered how the solid dissolves in the water? Well, if you look at a water molecule, it has this V shape. Because of that V shape, the electron distribution within this water molecule is not even. So then some areas of the water has more electrons than others. We call that polar. The polar nature of water can help to split the bulk sodium chloride into this invisible solution. Because of the electrical attractions, these water molecules will grab the ions, either cations or anions, apart from the bulk. So after the salt is dissolved in water, you will no longer see a condensed crystal of sodium chloride. Instead, you will see this freely floating around sodium cations and chloride anions. So that is how something is dissolved in water. And what we have as the salty water is not a pure substance. It's actually a mixture. So we call that a solution. When we talk about solution, we can distinguish the compositions into two parts. One is called solute. It's a minor component in a solution. The rest is called solvent. It's a major component in a solution. And for a solution, it's a homogeneous mixture. The word homogeneous means it's all the same everywhere. So in this water solution, salty water solution, every part is the same. You don't see crystal here, and everything is in the solution phase or in the liquid phase. So in this case, obviously we have less sodium chloride than water. So sodium chloride is a solute, water is a solvent, and the salty water is the solution. Sometimes when you dissolve a solute in solvent and make a solution, the electrical conductivity can increase. So based on that, we're going to introduce the concept of electrolyte. Here is an example of a light bulb with two posts immersed in a material. So on the very left is just the water. In the middle is sodium chloride solid. And on the right is a sodium chloride solution. So once we give power to this light bulb, the left and the middle picture, you don't see the light bulb is on, but on the right is on. And that's because on the left, there's no electricity conducting between those two posts. It's just the water. And water itself is not a good conductor. It's an insulator. In the middle picture, when you have the sodium chloride, because all the cations and anions are fixed and sitting next to each other, they cannot move freely, so they cannot conduct electricity either. On the right, when you have the solution, these dissociated or dissolved cations and anions can move freely in solution. So these can be the carrier of electricity, so the light bulb is on. So dissolved ionic compounds can provide moving ions that increase the electrical conductivity of a solution. Depending on whether its water solution is electrically conductive, a substance can be distinguished as electrolyte and non-electrolyte. The electrolytes are the one that increase the solution's conductivity, while the non-electrolyte is the one that does not increase the solution's electrical conductivity. So a few examples of electrolyte are here. So when I say salts, I do not just mean the sodium chloride. This salts is a general concept salts. That means it's an ionic compound with metal cations. Also, we have acids and bases. we are going to introduce these two concepts in later chapters. And examples for non-electrolyte are most covalent compounds, okay, such as glucose, alcohols, and fats. Within the electrolyte, we can further distinguish that into strong and weak electrolytes. As you can see here, the same experimental setup of the light bulb. Some solutions give very bright light. Some solutions give weak light. So strong electrolytes obviously are the electrolytes that greatly promote the electrical conductivity of a solution. So that usually means the salts and strong acids and bases. And its strong electrolytes 100% dissociate to ions in water solution. For example, hydrochloric acid can fully dissociate into hydrogen ions and chloride anions in water solution. So this is a strong electrolyte. For weak electrolyte, usually they are weak acids and bases. It only dissociates partially. So in the solution, it will have a combination of ions and molecules. Molecules refers to the chemical compound that does not dissociate. For example, carbonic acid. It partially dissociates. So you can see here, I use a double end arrow to indicate that partial dissociation. The table 4.2 give you the strong and weak acid and bases. So you can take a look at what are the strong acids, what are the weak acids. You need to know which one is strong electrolyte, which one is a weak electrolyte. Finally, let's talk about solution stoichiometry. For solution stoichiometry, like the stoichiometry we talked about before regarding a chemical equation or chemical compound, here solution stoichiometry, you can turn the subscript in a compound to the corresponding coefficient of the ion. For example, here potassium bromide, each of the potassium and bromide has a subscript of 1, which we usually don't write in the compound formula. So when dissociate in the water, it gives us 1 potassium ion and 1 bromide anion. For 1 mole of calcium bromide, that includes 1 calcium and 2 bromide. When it dissociates to the water, we can have 2 bromide anion. So that 2 in the bromide corresponding to the 2 of the subscript in the chemical formula. The same thing as here, aluminum sulfate. We have 2 aluminum and 3 sulfate group in the compound. So if 1 mole of aluminum sulfate dissociates into the water, we'll have 2 mole of aluminum cation and 3 mole of sulfate anions. So this is a stoichiometry, solution stoichiometry. Based on these dissociation equation, we can do the same stoichiometry calculations as we did before based on a chemical equation. All right, this is the end of this video. See you next time.